with. So even within our own solar system, we know that we have, amongst the rocky planets, a wild diversity of places, atmospheres, surfaces, sizes and masses, similar-ish, but they can result in very different scenarios. And if we were to observe our 3 rocky planets here as exoplanets, the main feature that we could see is simply their atmosphere, and we would be taking a spectrum of that atmosphere. And so for Venus and Mars, their main spectral feature is this carbon dioxide band down at about 15 microns. It's showing you one of, the main constituents of their atmospheres. Whereas if we were to observe Earth, we would see that CO2 feature. We would also see other features from water and ozone in this particular wavelength range. So a spectrum is a very powerful way of being able to tell the difference between different scenarios for planets that simply from mass and radius and even their density may look very similar. So the goal is atmospheric characterization for rocky exoplanets across the wild diversity that we see. Let's take a look at that diversity. I'm showing 2 plots here. On the left, you've got very classic orbital separation of planet versus planet radius. And on the right-hand side, this is a paper from plot from one of Angeli's papers, which is showing you the mass-radius relationship, where, sorry, that's radius on the y-axis there. And it's showing you some models, the curves for different different compositions. And what you can see for the rocky planets, so I don't know if you can see my mouse, but sort of, looking down here below, let's call it 2 Earth radii, that the range of temperatures that we're spanning here go all the way from about 170 Kelvin all the way up to 2000 or so. So we have this very wide range of temperatures to deal with. And so it means our planets are experiencing very different radiation environments. The TRAPPIST-1 system down here has an M-dwarf host, whereas 55 Cancri is more a sun-like host. So what do we learn from this? What can we find out about the diversity of rocky planets, be they lava planets or frozen snowballs? And what does that mean for putting Earth in context? That's really the goal of what we're trying to do. Okay. So at the same time, we have to recognize and appreciate that exoplanets are quite possibly some of the most complex objects that we look at in astrophysics. They're not one-dimensional dots. They are 3D plus time varying. So they're 4D objects where we need to model the chemistry and the dynamics of their atmosphere. So even in the simplest case of an ultra-hot Jupiter, you have intense radiation that's dissociating most of your molecules into atoms and ions. You may have some circulation, maybe you get some recombination and rain out on the night side, and you might even see some eastward hotspots and some westward clouds. And within this 1 pixel that we're looking at in our images that we take to get this information, that we're dealing with all of these different atmospheric processes. We have atmospheric escape, photochemistry, the thermal structure of the atmosphere, where there's clouds and hazes, the vertical mixing, any kind of circulation or other deviations from chemical equilibrium. And all of this is going on in exoplanet atmospheres. It happens in giant planets, and there must be similar processes happening in smaller planets as well, small rocky planets. And every wavelength that we can access as well gives us information for different processes. So the wider the wavelength we can cover, the better. So lots of information contained in a single pixel. Now, I'm giving a talk about high-resolution spectroscopy, but it would be remiss of me to not talk about JWST and the slightly lower-resolution spectroscopy that we're working with for this. So this is just to highlight the sort of extraordinary data quality that we have with JWST. And this has been afforded by its larger mirror and its exquisite dynamic range and sensitivity to mid-infrared wavelengths. So this is just showing you a hot Saturn, and this was a really nice confirmation of this huge peak here from this CO2 feature. And then at the time, there was a mystery peak down here that we now know to be SO2. And very beautiful light curve quality on the left-hand side here, all the way from sort of the optical down into sort of the end of the near infrared. For rocky planets, JWST is also doing well, but the information we can get out is a bit different. So the data quality here, in terms of the precision on the error bars, is actually better than what I showed you in the previous plot. The errors here are about 20 parts per million. But you can see the information is sparse, and this is a challenging object to look at. So this is looking at the super Earth 55 Cancri E, and it's a recent paper indicating that there could be an atmosphere on this planet, but the data isn't sufficient enough to really tell between different atmospheric scenarios. So there are some plotted here where you have a background gas of just carbon monoxide, or you could have a background gas of carbon monoxide with some CO2 involved, or you could have a nitrogen background gas with CO2. You can see that the data can't quite really distinguish between these. Now, we could take our JWST hammer and keep going at it and try and shrink those error bars down. And we can do that, and we might get more information to be able to tell the difference between some of these models. But there is more information in here if we were to use a different instrument. And if we could turn up the spectral resolution, we would find something quite interesting. So this is for one of those models. So this is the just having carbon monoxide as a background gas and having some CO2 at different levels in that atmosphere. I'm just showing you it's just those gases in that atmosphere. What you can see here, these are the H and K bands. So they span between about 1.5 to 2.5 microns. So we're a little bit bluer than the JWST data. But there are these really nice band heads down here of CO. And then over here, we have a mix of CO and CO2. And you can see that the JWST resolution for this model is shown approximately in the gray line. Whereas if I was to dial up the resolution here to 100,000, actually, no, about 50,000 for this, suddenly we get infinitely more information in these individual lines in that molecular band head. So previously, it's quite hard to see the difference. So within this region, there's both CO and CO2, and it's hard to tell the difference between the band heads. But if we were to go to higher resolution and even look at other wavelengths, we would be able to tell the difference between this. So this is something we're looking at to see whether or not current high resolution spectrographs can actually do this work. So that's in preparation with several of the students and postdocs here in Oxford. So with this in mind, let's have a look at CNC. Can we actually do high resolution spectroscopy? But, well, I can tell you why this might be interesting for this particular planet. So if we were able to tell the difference between these atmospheric scenarios for 55 Cancri E, depending on the amount of CO and CO2 that we would measure, so this volume mixing ratio here on the left, we would actually be able to tell between these different scenarios. So if we see lots of CO and no CO2, then we're over here on the left, we've probably got a CO-only dominated atmosphere. And that actually means we can say something about the surface composition of the planet as well. So this is representative of the abundances at the surface. And if we were CO only, it would mean we have a reduced surface, whereas if we had CO2 and a nitrogen background gas, so that would mean we would see lots of CO and well, if we're right over here, maybe we see lots of CO2 and no CO, but actually that surface is highly oxidized. And we can think about the timescale of how rapidly these sort of surfaces can be oxidized. We think on Earth that happened quite early on, but is it important for setting our atmosphere and even the emergence of life on Earth? These are things that we would like to understand, but that we can't quite get to just yet. But if we can start to break the degeneracies between these different atmospheric scenarios, then that's where we want to go. Okay, so high resolution spectroscopy. It's a bit of a challenge. So what are we actually trying to do? We want to go to high resolution, but the spectrographs to do so are currently too heavy to launch into space. I say currently, we should think about trying to do this. So for now, we must do it from the ground. And that means we need to look through the Earth's atmosphere. Now, our Earth's atmosphere contains quite a lot of water, and that impacts our spectra. It gets imprinted on top of it. So we need to learn how to deal with that. The second is that high-resolution spectroscopy spreads the light out across many pixels, and that means per pixel, the amount of flux you get is less. And so to counter that, you need a big mirror to get enough photons. But you're still going to have a very faint planet spectrum, and each individual line will be very, very difficult to detect. It's going to be hidden underneath the noise level. So we need to combine the signal of all the individual lines to actually be able to understand what we're seeing. But we can do this. So for those of you not familiar with the technique, I just want to quickly show how high-resolution spectroscopy actually works. So for short period planets, so things like lava planets, we would use the fact that they are orbiting very fast around their host stars, and that their spectrum is blue shifting and red shifting as they go around their orbit. If we were then to look at the spectral lines of the planet versus those of the star and the tellurics, star and tellurics are essentially stationary. That means that if we were to take a sequence of spectra over time, we could remove everything that doesn't vary in wavelength, and what we would be left with is our Doppler shifting planet spectrum. And you can see here that we're essentially tracing out the radial velocity curve of the planet with each individual line. Now, this is a toy model, so those wiggly lines that you see there, you will never see this well in the data. For rocky planets, they're buried way underneath the noise of the star and the tellurics. This is just visually. So we then go through a process of trying to clean out that telluric and stellar contamination, and it's a quite difficult process that is still ongoing as to how best to do it. And I am not going to talk about it at all. I'm going to skip over it, but please feel free to ask me questions at the end if you would like to know more. But in an ideal world, we would clean everything out, and we would then shift into our planet rest frame and sum all our spectra together, and we would get something like this. Very nice spectral lines, similar to the model that's shown here. In reality, we don't get that. We get something like this. It's basically noise. Each line there has a signal to noise of 1 or less. And so you might be able to convince yourself that some of those lines match up, but realistically, this is not going to work very well. So we need to find a way to combine them. And we do that by using cross-correlation. So we take our data, we take a model, and we scan it through. And when it matches, we get a peak in our cross-correlation function. Now, you can see immediately that this relies on you getting the model right. But if you do, it's an excellent way of actually boosting your signal. And we find that with high-resolution spectroscopy, you actually are able to reach contrast ratios of about 10 to the minus 4. If you were to combine this with high contrast imaging, you could actually push even deeper down to fainter planets. We'll come back to that later. So this is what we can do. In reality, what that looks like is we do it over the whole sequence of spectra that we have. So that's what you see in the top panel here. This is a small section of that planet radial velocity curve. And in the bottom, I'm just showing if I summed all of those together, you can see that they don't really constructively add. I need to shift into the planet's rest frame, align the signal and sum them, and then you can see that cross-correlation peaks. If you can't see it, I'll guide your eye like this, and hopefully you've noticed that there's a gap in the middle. That's a good thing. That's when the secondary eclipse happened, and so we didn't expect to see the planet here. So it's another good confirmation that this signal pre and post eclipse is really a real signal from the planet. So we can also explore the range of orbital velocities that we think the planet might have. We don't actually need to know this a priori, so it means that we can use this for non-transiting planets. We can make plots like this. So on that y-axis now is the velocity that I tried to shift it into the rest frame, and then I've summed everything, and so each row in this matrix is one of those summed cross-correlation functions. And so these are some of the original high-res detections showing you water found in the transiting planet HG 189733b, the hot Jupiter, and then another non-transiting hot Jupiter, Tau Bootis b, looking at carbon monoxide. the fact that these are non-transiting planets, you actually are able to measure an inclination from this, and that actually breaks your M sin I degeneracy for your mass. And so we're actually turning these into spectroscopic binaries. And knowing the mass of the star means that we can know the true mass of the planet and not just the lower limit. So actually, for some of these Earth-like planets, if we can do this, we're actually able to break that M sin I degeneracy and get the true mass, which will help us more fully understand what's going on in the interior once we know the density. So that's what it can do. And the field has grown enormously in the sort of 10, 12 years since these papers. And it's quite regular. I'm not going to say it's easy, but it's quite routine at this point to be able to generate an entire spectral atlas for your planet. Here I'm showing, this is one of the hot Jupiter WST-76b. This is work by Stéphane Pelletier. Just showing these really beautiful detections of lots of different metals. This is using optical spectroscopy for very hot planets or ultra hot Jupiter. So the information that we get from this isn't just detections of molecules. We can actually do more than that. But as I've mentioned previously, this really relies on the fact that we have accurate and precise models. That means the information from the line list that goes into the model has to be accurate and precise, and ideally complete as well. And that's quite a big ask from our quantum chemists and molecular spectroscopists to actually be able to do all of this work. So we really need to make sure that it's fully supported as part of the exoplanet atmosphere work that we do. One can imagine for the Earth, we can study the gases that we expect in Earth quite well. But as we start to change the temperatures and pressures, super Earth atmosphere might be something very different. The background gas might not be nitrogen. And so we really have to think about all the different changes the atmosphere we need to incorporate to get a good model for this. Okay, but assuming we have good lineness, we can proceed. And in 2019, Matteo Brogi and Mike Lyon introduced this likelihood framework that allows you to take a cross-correlation analysis, and rather than simply just having a detection of a molecule, you can actually get quite stringent constraints on the abundances and the CO. So on the left-hand side, we just have an example similar to what I've just shown you. But when we fold that into a likelihood analysis, we can actually get these constraints. So here you can see the C to O ratio over here on the right of 0.59, and then an error there of about 0.1 dex. So actually, this work for hot Jupiters is competitive with JWST in that we can achieve similar results for carbon to oxygen ratios and abundances for these ultra hot Jupiters. So we can do some of this from the ground. We can use this to have a look at what's going on in the atmosphere and see whether or not, for example, showing here whether the atmosphere is enriched compared to the protosolar values, and whether we can see any refractories, for example, that have been trapped, rained out on the night side, or whether anything has been strongly ionized. So we can really get into the chemistry of these atmospheres. And ultimately, in the future, this is what we want to do for rocky planets as well. Now, it's not just chemistry that we can learn about with high-resolution spectroscopy. We're actually sensitive to the line shape and the line position. And so anything that isn't accounted for by the Doppler motion of the planet's orbit can be an effect of the dynamics in the atmosphere itself. So, for example, here we're showing work from Sid Gandhi, who shows how, as you go through a transit, you're probing different parts of the atmosphere, and that your planet is going to rotate slightly as you go through the transit, and you're actually looking through different regions of the atmosphere. And if you have a look at the posteriors for the distribution of iron in this case, you can see that it's actually shifting depending on which region you're actually looking at. Similarly, thinking about the altitude, this is a paper from Aurora Casali and Haley Belts, showing that if you look at different strength lines from iron, you're actually, again, probing different velocities. And so as you go deeper into the atmosphere, you're actually probing the faster winds, the stronger winds from a jet deeper down in the atmosphere. So we're really starting to get at that three-dimensional structure using the high-resolution spectroscopy. We can also look at the rotation of the planet. So if we have a freely rotating planet, so imagine something like Beta Pictoris b, which is widely separated, it's not tidally locked. This has been done by looking at the rotational broadening that the line suffers due to the planet rotating. So you have one side of your disk red shifting towards you and one side blue shifting, and that spreads your line out. So this was found for Beta Pic b. It has a rotation period of about 8 hours. A more recent result from Lisa Notman was actually showing here that you have this double trail that was seen in transit. And that's explained as the effect of an eastward supersonic jet around the equator with actually some polar clouds, and that results in this line shape that gives you this double trail. We can even test to see whether or not tidally locked planets really are tidally locked. And indeed, we can find that the rotation period for HD 189733b is considerably longer than it is for the freely rotating Beta Pic, and within the error bars is to the orbital period. So there's lots of information to be had from these data. Everything I've shown you so far is looking at molecular lines, so we have many lines to add together. But if we reach a point where we can look at a single individual line, we can actually learn something about what's going on based on the processes that create that line. Here I'm showing the helium-1 line. This is work by Roman Allard for a warm Neptune. And this actually tells us about the atmospheric escape. People have used this line to have a look at what's going on in atmospheres, and for HAPI 32b, even actually generate an entire model of what this escaping atmosphere looks like. We're actually looking at the 3D outflows from the hot Jupiter. And ultimately, this is going to help us understand how to interpret what we call the cosmic shoreline, but seeing whether or not the atmospheres are escaping or not. So Earth still has an atmosphere. That's great for us. But these planets up here, it could be that their atmosphere has been completely eroded by the host star, for example, or lost to different processes. So the question is, where does this really happen? And is it likely that if we can observe, unfortunately, these are the easiest ones to observe, but perhaps it's these ones down here that we're actually really interested in for getting atmospheres. So it remains to be seen, but it's very exciting to be able to do this work. All right, so I've shown you what the high resolution technique can do. I've shown it has some advantages over what we can do with low resolution data from space. And I've shown you what we've done so far for giant planets, mostly hot Jupiters. I want to start pushing down and see how low can we go to actually do this work. So the rest of this talk will be basically adventures with the extremely large telescopes and seeing what we can do for rocky worlds. And I'll highlight some of the challenges and, let's say, promises of what we think we will be able to do. Okay, so let me start just by highlighting a few of what the extremely large telescopes, what their capabilities actually are. So the biggest one will be ESO's extremely large telescope. It's going to have a 39-meter diameter mirror, and it will be located in an extremely dry atmosphere on the Cerro Amazonas mountain in Chile. It's very close to Paranal. I've been there. It is extremely dry, so that bodes very well for dealing with some of that telluric contamination. And there'll be a whole suite of instruments, including METIS, Andes, Harmony, and in the future PCS, that will be able to do high resolution work. And the first light, and hopefully science verification, for METIS is scheduled for 2029. So that's 5 years away, which really isn't that long. It's sort of one PhD in a little bit. So if you're just starting out your PhD now, it's quite likely that your first proposals as a postdoc might actually be to use the extremely large telescope. What does it look like at the moment? These are two screenshots grabbed yesterday. So it's looking good. Things are growing, and this one on the right is showing you the mirror mount inside. So you can actually see the baffling, for the secondary support structures, and the actual mirror down on the bottom here. At the same time, over in the US, the Giant Magellan Telescope is being built. This is going to be a slightly smaller telescope. It's a 25-meter mirror. That's being built also in Chile at Las Campanas, so a bit further down the road from Paranel, I think. It's quite nice to notice on where the foundations are being built here that there's actually space for a second one there on the left, which I quite like the idea of. But the actual support structures are being built in the labs, and all the mirrors have now been cast as well. So things are ticking along. And development is happening all the time on the instruments, not just for the ELT and GMT, but also the 30-meter telescope as well. So we have a very exciting future ahead of us. So this is just to give you a selection of the high-resolution spectrographs that are scheduled for either proposed or actually being built for these 3 extremely large telescopes. So I'm going to focus on 3 of these today, mostly Metis and Andes for the ELT, and then I'll show you a little bit from Harmony, but also to note that on the GMT, we're particularly interested in GCLEF and MODIS on the TMT. And these all have variations of different high-resolution spectrographs, and you'll notice for Harmony here, we're actually a little bit lower. So I've been talking about 100,000 resolution, but this is more around 20,000. But I'll show you that we can still do some quite interesting things at that spectral resolution. Okay, so let's start with looking at what Andes will do. And this is work by Bibiana Prinoth, who did some simulations for just a single transit of a hot Jupiter to show you the kind of spectrum that we would get from this planet. And hopefully what you can see here is that these are individual lines in the molecular bandhead. If there are any fans of M dwarfs out there, you're probably familiar with what TIO looks like. Well, this is what it would look like in a planet atmosphere, and you see these nice bands going up and down. So you're really reaching the individual lines. The same here for the CO, which is very tiny wavelength range here. You actually see the individual lines for CO. So this takes giant planet atmospheric spectroscopy from everything I've shown you so far and basically turns it into what we do for stars. So when we characterize stars, when we take their spectra, we have enough signal to noise that we can look at individual lines. It's extremely powerful. This is the future for doing this for giant planets. We're really going to start understanding what's going on in those spectra. It will be harder, much harder to do this for rocky planets. So with rocky planets, we're still looking at doing the techniques that I've shown previously. So the cross correlation and the likelihood analysis. So if we can see individual lines, what can we do with that? What's the power of being able to study an individual line or even variations in the line profile on average? So one of the first things that has been proposed for this is to do Doppler imaging. So imagine you have a storm or a spot feature of some kind on your planet that's rotating in and out of view. As it does that, it will block some of the blue shifted light, some of the red shifted light, and over time, you'll get a change in the line profile. But you could also imagine this as a transiting exomoon. So if you were able to isolate the light of the planet, you would then be able to wait and see whether or not you have something pass in front of it. And so this is something that I've been trying to develop over the last few years. This is working with Ben Sutcliffe, who was a student with me who's now in Edinburgh. And this is using vector apodizing phase plates. And these are tiny little optics that sit in your filter wheel that, through what seems like magic, but is actually very complex and very clever, delay pathways in your optics that actually generate you a point spread function of your star. So this image in the middle here, it's an image of one star, but you get 3 point spread functions. And in the top and the bottom one, we notice that on one side of the PSF, that the starlight is very deeply nulled. And so if my planet was sitting in one of these dark holes, I would actually be able to isolate the planet from its host star. And I also get what we call this leakage term here. It actually acts as a reference. So I could compare how the flux of my planet was changing compared to the host star, for example. And if we know the host star to be stable, it provides us with a reference. If we could project that down onto an integral field spectrograph, we could actually then have a high resolution spectrum of the planet. If we were able to take a spectrum of planets sitting in the star hole, we could monitor these line variations. So the dream is that from the ground, using this approach, we would get light curves like this, as we saw from JWST. In reality, we probably won't ever get them quite that well, but we can see how close we can get. So this is the work that I've been doing with Ben. This is looking at a relatively large companion to an M dwarf, using the LBT with its vector apodizing phase plate and integral field spectrograph. So every pixel in this image has an associated spectrum. This is the summed image over the course of a whole night. Individually, you don't see the companion on the right there, but I can show you where it would be here. And so we put apertures down on the star and the planet and try to create a light curve, a white light curve. So even though we have the spectral information, in the same way that we bin up JWST spectra, we're doing the same. We're actually creating a white light curve here. And this is what we got. So you can see the raw data at the top and our sort of final light curve down here, binned up in 15-minute bins in red. And potentially there is some variation here. We did see some potentially sinusoidal variability, but we would need more data to confirm this. So we went back and we have a second night, which within the error bars is completely flat. But the precision is repeatable at about 4% level. So it's entirely possible that this is a real evolution of a fairly rapidly rotating low mass companion to an M dwarf, but more information is needed before we can claim anything particularly strong about this. But the key point to note here is that we can get this repeatable precision of about 4%. That's not enough yet to get down to exomoons. We need to be down at least 1% and probably lower to do that. But it's promising. And I think if we can understand these techniques before the ELTs come online, we potentially have a way to look at companions to giant planets, maybe even giant planets in the habitable zone, where maybe their exomoons are potentially habitable. And this might give us a way to study the very tiny rocky worlds that orbit giant planets out there around other stars. Okay, so the big thing for the ELTs is really thinking about whether or not we will find biosignatures, signs of life. For METIS, which will be the first light instrument, this will be between 3 and 5 microns. And if I have a look at the Earth spectrum between 3 and 5 microns, you can see we have nice biosignatures all over the place. And I'm just showing you a very crude comparison here between a resolution of 100. So you can really see all that information, that extra information that we can get by going to the higher resolution. However, 3 to 5 microns is hard to do. I'm showing you here the telluric contamination in that wavelength range, and importantly, how the sky background changes. And you can see as we go to about 4.2 microns, there's a sudden jump in the sky background, and that just gets steadily worse. And so in the end, we reach a point where even though we're taking, we could take longer exposures, our flux from our star can be completely dominated by the sky thermal background. So we want to be able to use METIS on the ELT, but the question is how far down in wavelength can we push it? And up until Luke's work, we'd only got down to about 3.8 microns. So Luke observed beta Pic B, this freely rotating planet, with CRIRES to see if we could use cross-correlation to actually pick up the signal of the atmosphere between 3 and 5 microns. And the good news is that we do. You'll notice that these plots here, they're no longer velocity versus orbital velocity, they're just velocity versus separation. And so at the star's position, we don't see any peak in our cross-correlation function, but at the planet's position, we do. So we can interpret that as being our planetary signal. So we see carbon monoxide and water. And interestingly, potentially, we maybe see SIO in this giant planet, which is nominally expected from modeling. But we're getting follow-up data to see whether or not this feature down here is real. We could argue that there's some similar strength features elsewhere in this plot, so we really need to follow that up. But SIO is important because it enables you to actually look at the solid to gas accretion ratio during the formation. So it's important for giant planets, but also for rocky planets. We're very much interested in SIO as one of the main constituents that we might observe in the outgassed atmospheres from lava worlds, be they silicate dominated, so sort of really rock vapor atmosphere, or whether there's volatiles in there. Being able to access that SIO can really help us start to understand that atmosphere surface interaction and really try to see whether we can understand more about the outgassing of secondary atmospheres like the one that formed on Earth. So we've been able to do this with CRIRES for a giant planet. What does that mean for trying to do this for smaller planets with METIS? On the left, I'm just showing you how the contrast ratio changes as we move further away from the host star for different wavelengths. And you can see it changes quite rapidly. However, with METIS at the ELT, we get a d to the 4, so that's the diameter to the power 4 reduction in the thermal background noise. And that's just simply because we have a larger mirror, so we get more photons, and we're observing over a tiny area of the sky. And in fact, we do about 8 times better with the same observations, or we could do these observations with less than 2% of the exposure time. So we could do all of this, what I've shown you, in about 30 seconds with METIS, which I think is incredible, and actually shows you that time monitoring, the time domain study of this is possible with the ELT. So if we had a few hours to watch a planet rotate, we can do that at high spectral resolution. All right, so let's walk it down. Can we go any further than giant planets? Can we get to the sub-Neptunes? Sub-Neptunes are a really fascinating area at the moment of exoplanet atmosphere work, and they're on the way to really rocky worlds, and they're completely enigmatic. We really don't quite know what's going on. There's lots of theories and lots of debate in the literature at the moment. You're seeing here a JWST spectrum of sub-Neptune. We actually see some features, which is interesting because we potentially see lots of clouds on sub-Neptunes. But the question then is asked, what is going on in that atmosphere, and what does the core of the planet look like? Or do we have silicates? Is there a liquid water atmosphere? Is there a miscible atmosphere between hydrogen and water? So really being able to see what's in the atmosphere is really important. And we can play the same trick again. Can we go in with the high resolution and see if we can actually pull out some of these molecular bands? The other important thing about high resolution is that we can actually still see the gas above the cloud deck. We have that high resolution, and so the cores of the lines are pointing up above our cloud deck. And in principle, high resolution is sensitive to that. So Luke has been busy again. He's been looking at a sub-Neptune. And this is just to show you some of the challenges of doing this. So in the orange here, I'm showing you, this is an M dwarf host star. So we have the spectrum of the M dwarf, and on the bottom you have the spectrum of the sky. And you can see that our CRIRES data is a very good combination of those things. The planet we're looking at, if we expect water, potentially is dominated by water in the host star, or even other species in the host star, and the water from the tellurics. So if I was actually to do my cross-correlation without first cleaning that data, I would get a matrix that looks like this. And actually the planet signal, where you see the brightest point there, is actually quite close to where we expect to see the planet at this cross. And you might perhaps think that, oh, maybe I've got a signal. But actually, one side of this feature is formed by the tellurics, and the other side is formed by the star. So we have to be extremely careful in making sure that we very accurately remove both the tellurics and the host star. So that's what Luke has been working on. So we're looking at GJ 3090. We're just showing here, in terms of period and radius, the diamond shapes that you see here are all planets, the sub-Neptune planets that have been, or things less than a Jupiter that have been studied at high spectral resolution. And it's only the HAPI 11 that actually has a detection. Everything else is upper limits. And just put it in context with a few other well-studied objects from JWST and Hubble. So what do we see? We're still working with upper limits. Okay, so on the left here, this is actually our observed data. And you can see that we're not really getting any detections, but for a model injected 1 bar cloud deck with 10 times solar metallicity, we actually would have very strong detections. So the atmosphere has a very good constraining power. So we're working on getting the upper limit set for this, but I think it's showing us that we can actually do quite well with high resolution for the atmospheres of sub-Neptunes, even if we're not making direct detections. Okay, so just to finally wrap up, the key driver for the next frontier of exoplanet observations is reflected light. This is what's driving the Habitable Worlds Observatory and really lots of those high-resolution spectrographs that are pushing into the blue band with the ELTs. You can just see on here the different contrast ratios and temperatures, the kind of separations that we're working with. So for the VLT, we're limited to things sort of to the right of this dashed line here. You can see that Proxima b, our nearest exoplanet, is just on the edge of that. But for the ELTs, we're really starting to get down to some very interesting targets indeed. So the contrast ratios that we'll probably be able to reach are about 10 to the 7. And we're interested in particularly in these cool ones that are approaching Earth-like temperatures. So how do we do that? There's quite a few instruments that we can use for this. And we want to look at their reflected light. We have to remember in reflected light that we're not just looking at the planet's absorption spectrum, we're looking at stellar reflected spectrum as well. So we have to be able to combine those two. But just to note, from reflected light spectra, we can learn things like the energy balance, the scattering properties, possibly even surface structure from glints off of oceans. And we also learn about the atmospheric composition and possibly even biosignatures. And I've noted lots of these for the Earthshine spectrum of Earth. So far, there is no robust detection of reflected light with high spectral resolution, but we can get down to contrast limits of about 10 to the minus 6 for looking at hot Jupiters. We are trying to look right now using the 16 meter effective meter mirror mode for espresso in full UT mode to actually look at a hot Neptune to see one that's particularly reflective to see if we can actually do this work. So we'll keep you posted on that. Sophia Vaughan, who's just moved to MPIA from Oxford, has done some simulations using Harmony, which, if you remember, had a much lower resolution, down at about 18,000, that she can simulate the point spread function for Harmony, which projects again onto an IFU, reconstruct that and actually recover a rocky planet. This is an approximation of Proxima b, but it's been put much further out. Proxima b is actually down here underneath the focal plane mask. But even at a resolution of about 18,000, we can still actually do this work. We have enough information to pull out the planet spectrum. In this case, we need to modify the focal plane mask, which we're working to do at the moment, that would enable Harmony to actually do this work. With Andes, however, where we have that 100,000 resolution, it's looking very promising for a very precious sample, this golden sample of nearby temperate rocky worlds in reflected light. And we can even estimate for Proxima b, for example, if I took a 1 bar Earth-like scenario with or without clouds, you can see, for example, how many nights it would take me to reach a detection of O2 or water, for example. This is on the order of sort of 50 nights or less. And finally, with METIS, this is one of the original simulations that's been updated. That shows we can see Proxima b at about 3.8 microns with METIS as well. So we have this enormous suite of instruments that are capable of giving us this sort of 1 to 5 micron deep high resolution characterization of a rocky, very nearby rocky exoplanet. So I'm going to leave you with this one thing. And this is a plot from a paper by David Singh that came out just a few days ago. And you might need to squint or move away from your screen a little bit, but I hope you can see here that as a function of orbital phase, this is a cross correlation using a resolution of 3000 from JWST. And I hope you can see that it actually traces out the full radial velocity curve. It's a full phase curve data set. You can actually see the cross correlation trail actually gives you that RV. You can see that in the eclipse, it disappears, and you can actually potentially see it invert here as it goes through the transit. So cross-correlation, even down at a resolution of about 3 to 5,000, is possible. There's information to be had here. And it is possible to launch spectrographs at this resolution. They're much smaller and much lighter. And so this is potentially an avenue for the Habitable Worlds Observatory to really squeeze all the information that it can out of those targets that it's going to look at for rocky worlds in nearby rocky worlds in reflected light. Okay, I will finish there. That's me at the ELT. That's my conclusions. I'll leave them up and I'll take questions. Thank you.
Thank you very much, Jayne, for the very exciting talk. I think high resolution, especially with ELT, will give us a lot of new science in the future. Are there any questions? We have some time, maybe a few quick questions. Leonie, that was... I mean, I can start. So obviously 55 Cancri was observed with high resolution several times.
Yeah.
And you talked about it at the very start of the talk.
Yeah.
I wonder, in the future, is there any expectation that we will detect something there? Now that James Webb has, kind of hinted maybe for an atmosphere.
Yeah. So we've been looking at this, and I think it's possible with existing spectrographs. I think the previous high-res observations have been in the optical, where I think it's much harder to do. But if you go down into the K-band, like I was showing, where you have that CO feature, then I think, depending on how big your mirror is, but I think there is potential to actually do that for 55 Cancri E. So I think it's a very exciting prospect to be able to put that along with the JWST data.
Yeah, the one question I have about so I'm not an expert in high resolution, but what are the theoretical bottlenecks? For example, when you look at 55 Cancri, you might expect a very complex atmosphere with lots of molecular lines.
Yeah.
And I don't know if it's the line lists that might not be accurate enough, it's the chemistry models. What is kind of like the concern when it comes to high resolution there?
I mean, I think with existing instrumentation, it really is still being able to get enough signal to noise is going to be a limitation on that. Hopefully with the ELTs, that it will be a very easy one to do for the rocky worlds. So yeah, then it's a case of, do we have, I think the line lifts are going to be important for this, given the temperatures that we're talking about, sort of almost 2000 Kelvin. So yeah, I think that will be one of the potentially main bottlenecks for doing this. If we've figured out how to do good telluric removal by that point, yeah. One thing I didn't talk about was there seems to be a level of variability with 55 Cancri E, whether it's the planet or the star. I don't know, but I think that's something to think about and possibly simulate for high resolution to see whether or not potentially stellar variability could impact or not.
Yeah, exactly. I think I'm not sure how good high resolution is at detecting variability or how difficult it is to distinguish it. But that's something that would be very useful for 55 Cancri.
Yeah,
if we can do that.
If the planet itself really is varying, I think we're in the same situation. So keep going back and looking. But if it's a cloud thing, it might be that we're still sensitive to lines that maybe the lower resolution wouldn't be sensitive to.
Okay.
So yeah, it'll be interesting.
Anyone have questions? You can raise your hand or just unmute yourself. Leonie, you have a question?
Yes, I have a question actually now. Yeah, so I'm always curious about clouds. So I was wondering if high-resolution can help with, could help, for example, also detect some features we could have at lower wavelength that like don't really fall in the range of JWST, because I find that it's quite hard to actually distinguish the different types of cloud features we have like in the infrared. So yeah, maybe you can say something about that.
So you're asking if we go to more optical wavelengths?
Yeah, exactly.
Yeah, so this is what we're hoping that the reflected light work will do with the high resolution that we, in theory, if you have a cloud deck that is going to sort of cut off your bottom of your lines, and so it will change your line depth and the ratios between those lines. And in theory, the high res is sensitive to that. So when we go looking at the reflected light, we can include the clouds in the model and generate the spectra. So we can actually use that as a parameter in the fitting that we do with the modeling. So that would be the optical wavelengths, but I think you can also do that in transmission as well. But yeah, I agree. We need to go into those optical wavelengths at all resolutions to really understand what the clouds are doing. With the high res, you're kind of limited to between sort of about 0.35 and 5 microns. That's the range that we can do. After about 5 microns, I think that background gets too high. Yeah.
Avev, you have a question?
Yeah, sure. Thank you for this very interesting talk. I want to ask a question about the trouble when you have too much of a good thing. In multi-planet systems, you can start to have the problem of contaminating planets. So you can no longer maybe assign the information to a single planet, or the other planets may be interfering with the interpretation of the target planet. So this can be a problem.
So I think that would be mostly a problem for the closer in planets where we're using the Doppler shift to get the information. However, in theory, what should happen is that because your planets are moving at different orbital velocities, that when you make that KP v cis map, that your signals would be at a different KP. I'm not even sure they would phase correctly on that plot. So you potentially do have some contamination, but because it's a very specific orbital velocity that you're interested in, you have some counter to that. There's some robustness in that the velocity tells you which planet you're actually looking at.
Okay, in this particular technique, yes, as long as you're doing cross correlation, then you can disentangle this. Thank you. Yes.
Yeah.
Maybe one final question, if anyone has one. Tonmoy, go ahead.
Yeah, thank you, Professor Jayne, for the exciting talk. I mostly work on retrieval, so I was wondering about like when we feed the different kind of models to the data. So suppose we have different models and we have degeneracies among them. So there are some statistical, methods to compare which model is the best. So how confident are we in terms of the statistical methods? Like, are we like, do we have any new methods to statistically determine that this model is the best fit? So, yeah.
Yeah. For the high-res work, using this, we have this likelihood framework that allows you can test many different models, but of course, you're only really comparing how do those models compare to the best matching model that you put in. So if you're confident that your parameter space that you're exploring does encapsulate what's going on in the atmosphere, then I think we are exploring quite well the different models. But if you're not confident in that, then yeah, it's hard to say from there.
Okay, I think that's all the time that we have today. Let's thank Jayne again for the wonderful talk. Thank you so much. Very exciting stuff. If you could let me share one slide before everyone goes. So next month, we have Joshua Christensen from the University of Washington talking about atmospheres around and dwarf planets. And specifically, I think he will argue about potential atmospheres on TRAPPIST-1 planets. So don't miss that. Take note of the change time, which is at 4 o'clock UTC. Yeah, and I'll see you next month, I guess. Thank you for joining today.
Thanks.